And we're up and recording, ready to go. So it's Tuesday, August 24th. Here's our agenda. You guys are getting your labs out from yesterday. You guys got all your data yesterday. We're going to put together the graphs today and interpret those. Before we do that, I want to talk about your upcoming homework assignments. So I just passed you guys out this quarter page right here. It's just, now be really careful because there's a similar one floating around. I should have labeled these better. That has like 2 boxes. You guys see 2 boxes versus 3. Right. The 2 boxes is my honor, so it's not for you guys. But the one has 3 boxes. Okay, you guys see that one? Everybody's got one of these? Who does not have one of these? Except, okay, we get you one. Oh, you got the next one? Okay. Right, you guys good? All right. So, take you guys over this. So I wanted to get you guys some homework that was respectful of your guys' time, because I know we all have limited, scarce time that's very valuable. But also give you guys good opportunities for independent practice. And I think it's pretty much nails that goal. So got 3 assignments listed here. You guys see some due dates coming up. So first one says linear motion homework. On paper, solve at least 8 of any of the following. And I'm drawing from 2 sources. So the first bullet point says there are 10 2-part problems from the page with the boxes. The page with the boxes refers to this page with boxes. You guys remember this page that I gave you back on Friday? Okay, so you already have this one. Also, all these are on Google Classroom, so if you lose them. Okay. Right, so these are a bunch of math type, very basic linear motion problems. I'm going to go over some of these in class. I'll be referring to this page to get you guys started. Now, these are very formulaic. They actually involve lots of every single kind of basic scenario that you could possibly have. If you look at all these boxes have 5 boxes, and they choose 3 starting values. If you know little statistics, 5 choose 3 or 5 choose 2, you can only get like 10 different scenarios, and those are like the 10 scenarios that you can possibly have. So every single possible scenario is basically listed right there. I'm going to draw from those. The other bullet point says, well, refers to pages from college physics. Now, this one is clipped to the front of your desk. You guys see the front of your desk? You guys see a page that looks like this? All right, so get that. That's for you. Right, if you lose it, it's on Google Classroom, so it's there. You guys got this? Right, now, I should have labeled chapter 2 at the top. That might be a good idea because you guys can get some other pages that also look like this that are other chapters. So, might be a good idea to write chapter 2 at the top. Right. Now, these are from a college level textbook, which, of course, you guys use it because you guys are AP. Now, these are a little bit higher level thinking than those box page problems, a little bit more abstract type questions. I will also be drawing from these questions in the notes in the next couple of weeks and solving those. Now, how I usually do notes and how I'm planning to do this is I'm going to draw examples from both of those pages that I just pointed out, but I'll usually change the numbers so that you have a model to follow. You can say, oh, here's exactly how this is solved, but now I have my own numbers and I can try it myself, right? Like independent practice kind of thing, right? And at a minimum, all I'm really excited is for you to write out 8 of these on paper. I guess if you really want to keep it real bare bones, then you can follow along in class and I'll be doing stuff. You can follow and be like, hey, here's how this, right? But if you really want to learn this material really well and get especially well prepped for the AP exam, then I do encourage you guys to maybe look at some of the other problems. Maybe try some that maybe I didn't do in class that you'll have the skills for, but maybe require a little bit more creativity, since they're maybe a little bit different. Yeah, there's going to be plenty of problems and not enough class time to do them all, so I'll do as many as I can and you guys will have some more. Okay, so that's due Friday, September 3rd. That's not a few days Friday, that's like a week and a half from that Friday, okay? And by then, I'll have done enough in class that you guys know how that goes. Okay. Next one, AP Classroom, Unit 1 progress check. Now, Unit 1 involves both linear motion and also projectile motion. Right, so I put this due date off till Tuesday, September 7th. You guys know that Monday, September 6th is Labor Day. Gonna have a 3-day weekend coming up pretty soon. Okay. So now this has been open for a while now. I even saw that some of you guys have already started to dig around there and look at some of the questions. So you guys got plenty of time for that. But I do want to go over the most missed questions this particular week. So turn in by them so that I can go over the most missed questions. Now, these are multiple choice. Now, something I want to say about these multiple choice questions. I usually assign multiple choice for the AP for homework. There's an easy way and a hard way and a good way and a bad way to do this. So the easy way, which is not very good, would be something like this. Like saying, maybe just want to knock this out, get this out of the way, which is already a bad mentality for homework. Because the idea of homework is that it's an opportunity for to solve puzzles for independent practice, right? Right, so if you go in there saying, I just want to knock these out, and I'll just choose C. This one, I don't know, just choose B. Or, you know what? This one, it feels like the answer should be A, so I'm going to do A. This one, it feels like it should be C, so I'll choose C. This one feels like D. Like, if you're constantly going through problems saying like, it feels like it should be this, it feels like it should be that, you're gonna feel like you're getting a lot of them wrong after you get your score back. But if you do this approach instead, say, you know what? Griffin showed me a framework to solve these, and I have equations, I have models to think about. Maybe I have some graphs I can refer to. Maybe I know how units work, and I know that this property of this graph is like some area of a graph or some slope of a graph, right? Or there's some framework or equation, right? And I apply that framework, right? And I take my time and really think deeply about how things work, right? Then you will be pretty good. Right? Now, of course, that takes longer, it takes more time to do it that way. But if you do it that way, you're going to get budgets right, and then you'll know that you'll be prepped for the exam in May. Okay. After this, I went ahead and also threw on projectile motion. Very similar idea. There's a couple pages I'm going to be referring to. Now, these I have not given you the physical pages yet, but they are uploaded to Google Classroom. So if you want to get a sneak peek, look ahead. Then those there. Got another due date, September 10th. All right. So you guys get that? What's upcoming? Yep.
How do you grade progress check on each class?
Oh. Yeah. Great question. How am I going to grade the each classroom progress check? Right. So 16 multiple choice questions. I create 2 columns in focus. One column is out of 16 points, and that's just your raw score. So if you get like 10 out of 16, then I'll type in 10. Right? But that will not affect your class grade. Right? For the class grade, just if you did it on time, I'll just give you the 20 points. Okay?
Will we go over them in class?
What I usually do is bring up the questions and go over the most missed questions. So out of 16, there might be like 10 or 12 that maybe there are like 4 or 5 that pretty much everybody got right. So I'll tend to focus on the 10 or 12 that a lot of students missed. And then if there are questions about the other ones, then you guys can ask me. Usually how I do it. Okay. Yeah. So great questions there. All right. Any other questions about these? All right. So you guys ready to move on to the lab? Lab time. Lab time. All right. So yesterday you guys had a bunch of data for what were you getting data about? Go back. Quick refresher. Rolling cars down inclines. The question that kicked this whole thing off was, I wonder if there's some just general equation that links these 3 variables: the mass of the car, how far the car rolled, like distance, how much time, tick, 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 have been rolling for, right? What could relate those 3? I think it starts from rest and stuff, right? And think about how labs work, independent variables, whatnot. You really have to split this into 2 separate experiments. They will, how does the mass of the car strictly by itself affect the rolling time, right? Controlling for the distance. And then a completely separate experiment saying, well, let's control the mass instead and choose different distances and say, what's the ratio between distance and time? And then maybe we can put those back together all at the end. Okay? Right, so that's our thought process. That's the approach. Right? 1 independent variable at a time. Let me switch my screen over, present screen to share. Right. And you guys are period 5. Yeah, you got it. Okay. Oh, getting some. So real fast, about to ask for a volunteer for data, and also you guys remember I had you guys do a lab write-up on the back, right? So since you guys are AP, we're going to go over that lab write-up on the back too. So yeah, that'll be in about 10-15 minutes. Okay. So volunteer, who was changing out the mass of the car every time and feels pretty good about their data? Who feels pretty good? Change out the mass of the car. Mass of the car. Okay. Yeah, Melissa, what were your different mass values?
Our first mass value is the car is 35.0 grams.
35, right?
And then the next car is 42.4. The next car is 55.1. Then 135.5. And then 235. And then the last one you can get the weight thing.
All right. Technical difficulties. Okay. So like, you put the kilogram on it? Yeah. All right. Got a fun car. Bunch of inertia. Fly through the wall. But no time. And what were the corresponding times?
The averages are like
Average. Okay.
in order there's 3.06.
3.06,
3.01, 3.86, 3.68,
2.86, 2.68, okay,
2.77.
that's let's choose something. All right, that is pretty much what that graph should look like. Okay, so if you did this version of the lab, then you might have the graph already. So if you do, then good to go. If you don't yet, like let's say you did the other version, then here's your data. You guys can all get this graph. Okay, we'll talk a little bit about graph rules while some of you guys are copying this down. So in general, what's the rule for which variable should go on the horizontal axis? Independent or dependent?
Independent.
Yes, independent. So usually the independent variable. But you know what? There's some other graph rules, and there's actually a rule that overrides that. That says if time is involved. So there's a rule that says if time is involved, that is a rule you always put time down there, regardless of if it's independent or dependent variable. Okay? And that happened in this case. So you guys see how I've got time in seconds as the horizontal axis. Okay? Now label that on your paper too. So put time in seconds. When I eventually flip the screen back over, I'll do it myself so you can see. Oh, yeah, go.
You did it wrong already.
Yeah, okay. If you already drew a graph, but you flip the axes and count backwards, that's okay. I'm not going to count off. But for the future, you guys know that time goes on the horizontal axis. Okay, so for the future, you know. Okay. And then I'll have looks like mass and grams on the vertical axis. In this class, we usually do kilograms, but today we'll just do grams. Okay. So let me go ahead and wait, what's mine? There's something here. Here's, no, that's not it. Bummer. That's right. Okay, I'm gonna flip the screen over real fast and just show you what I mean by labeling the axes. Okay, so you guys are doing this one here. It says mass versus time, so I'm gonna put mass in grams and time in seconds. Of course, you guys are also gonna put some numbers. Starts at 0, 0, and then scale it from there. Right? You guys have some points. Put the points where they go. And then, what about line of best fit? What basic relationship does that look like? You guys were thinking it was basically a vertical line. Does it basically look like a vertical line? Right? Okay, let me flip back to computer screen. Okay. Okay, so if that's true, then vertical line, what does that mean for the data? That means that for a car of any mass, isn't it pretty consistently taking about, 2.5 to 3 seconds to travel down the incline? Right? That's what that means. What that means then is that mass does not affect the motion of the car. Right? So whether you have look at these different masses. If you go from 35 grams to 200 something grams, that's almost a 10-fold increase. Not quite, but almost. Right? But the times barely changed at all. It's pretty steady. If you have more data, let's say you have like 10 points, 15 points, it was pretty well lined up into just a vertical line. Okay? So when we get to that question at the end, it says, what is the distance of the car as a function of all the other variables? Is mass even going to be part of the answer? Nope, not even going to be the equation, because it doesn't matter. Heavy car, light car, they all sound the same. Think of the other classes they wrote that, because there's my second period, there's my first period, so over and over again, it's like pretty much, here's my last class, and here's you guys. And so over and over, you see basically a vertical line. Okay. You guys ready to move on to the next graph? Okay. So X versus T? Oh, yeah, go ahead. Oh, I thought you raised your hand. Okay, so X versus T. So what's the relationship between distance and time? Now, the way I had you guys hypothesize yesterday, we did some hypotheses for all these yesterday, was if you double the distance, does that also double the time, or does it more than double the time, or less than double the time? Well, let's see what the data says. So who wants to volunteer the data? Who thinks they have pretty good data for changing the distances? Okay, anybody got data? Oh, okay. Mauricio, what were your different distances?
Okay, so 40,
40,
80,
80,
100, 120,
120,
yeah, 140, and 160.
All right. And what were the corresponding times?
1.32, 1.73, 1.81, 1.41, 2.34, and 2.35.
Huh, interesting. Guys, like an interesting looking outlier over here, but besides that, it pretty well looks like a pattern. What was this one? 120 years? Okay. So just for trend line purposes, I hate to do this, but I'm gonna ask that outlier right there. But if you ignore that outlier, then everything else pretty much lines up, doesn't it? Get that? All right. So same as before, scale and label those axes. I'll do it on the, I know you guys can't see my projection right now, but you do the same thing here. So you say, okay, on the vertical axis, X in centimeters. On the horizontal axis, I've got time in seconds, just like the last graph, time in seconds. Okay. Start out at 0, 0, scale those accordingly. So looks like the time's taken on like half second at a time, and the distance is like 20 centimeter intervals, something like that. Okay. Okay. Those points about where they go. Okay. Now we got to figure out what relationship we're looking at. Okay. Now, if it had been the scenario, remember when I was having you guys hypothesize that if you double the distance, if you think that that would also take pretty much exactly double the time, that would be shown by a linear relationship, right? If this were linear, like 1 to 1, then if you double one variable, the other also gets double. Okay. Okay. Right, you guys ready to delete the outlier? Okay. So this is bad science practice, but just to make this a little bit clearer. Okay. Just focus on those. Okay. What if I start by assuming that that's a linear relationship? I mean, at a glance, would you guys say maybe at a glance that could be linear, maybe? Okay. Kind of looks like it. Okay. Here's how you do this on Excel. You're gonna right click, go down to add trend line. Then, okay, well, just graphically it looks like that, right? Okay, so that looks pretty good, I think. But, ooh, wait, or does it? Okay. Because what if you extrapolate this all the way back to the origin, or supposedly, let's see what happens. If I extrapolate all the way to left, just keep going left, wouldn't this have a massively negative y-intercept? In fact, I can show that as an equation by hitting this box here. It says display equation on chart. It's this equation right here. Okay. And see this intercept of negative 100? No, guys, in this class, we also care about units, not just numbers. This is negative 100 what? Centimeters. Yes, negative 100 centimeters. That's like a full meter stick, isn't it? Okay. What that would mean is that at time 0, as soon as you let the car, as soon as you release the car, it jumps back a full meter? Is that what happened? The car jumps off the track 100 centimeters? That's how you would interpret this if this is truly a linear relationship. Which might make you say, huh, maybe it's not so much a linear relationship. Because there should be a point here at the origin, shouldn't there? Like 0, 0. The car started out point 0 at time 0. Okay. So, if you, let's say went back to the lab and got more data, or put a point right here. Either way, say, this might not be a straight line. This might be a what kind of shape? Starts with a P. Parabola. I guess it's a parabola. Oftentimes it happens with parabolas. If you just get a bunch of points like out here on the wing, it looks linear until you really think about it. Like, not so bad. So I'm going to show you guys a trick to determine if it truly is a parabola. Maybe it's a parabola, or maybe it's part of a cubic. Maybe it's part of like x equals t cubed, or t to the 4. Right now, how do we really know? Okay. How can we really test if it truly is a parabola shape and not some other kind of shape? Right. Well, here's what we're going to do. I'm going to take you guys through a process called linearization. So if you're looking for a title for this in your notes. Okay. And the process I'm about to show you right now, AP Physics, they really love this process, and you're going to want to know this because it's going to, well, if nothing else, it's going to get you a bunch of points on the AP exam. Okay. I'm going to do a very, very basic example. So basic, it's, never mind. We're good. Slightly. Okay. Let's do this. Let's take this equation. Y equals 2x squared. Okay? Can everybody look at that and tell me if that's going to be a parabola? Right? Okay. If you were ever really unsure, you're like, I don't know. can you always just make an XY table and figure it out? 0, 1, 2, 3. Right, so y is 2x squared. So x squared would be 0 times 2 is 0. 1 squared is 1 times 2 is 2. 2 squared is 4 times 2 is 8. 3 squared is 9 times 2 is 18. Something like that. And you can plot a bunch of points. So go x-axis, y-axis, 1, 2, 0, 1, 2, 3. That's like on the x. Y goes up to 18, 5, 10, 15, 20. Okay. Got a point 0, 0. Got a point at 1, 2. It's right about there. 2, 8. It's right about there. 3, 18. Right about there. Oh, that looks like a parabola. Okay, so that's all fine and good. Okay. So again, to go back to the physics side of this, what if you have the points, but you don't necessarily have an equation, you're trying to figure out the equation? Okay? So this is where the linearization is going to come into play. Right? Now, why do I call that linearization? There's nothing linear going on there. Right? That's it. What I'm going to do is I'm going to manipulate one of the axes, and it's going to cause all these points to line up in a straight line. Okay? You guys ready to see this? Okay. You guys' brains are turned on, right? Because this is a really important concept. It's going to keep coming back in this class. Right? You guys all have your coffee this morning? There you go. You know, I didn't start drinking coffee until I was in college. I was taking a 8:30 in the morning Top 3 class. And yeah, that class made a whole lot of sense once I discovered that brew. So what I'm going to do is, instead of doing y versus x, I'm going to do y versus x squared. Notice how I manipulated the whole axis, right? Is that, let me make a new table in case you want a side-by-side table to compare those two. So let's have x and then x squared and then y, and then maybe compare those. Right? So x will be the same 0, 1, 2, 3 as it was before. Right? Go ahead and square it and see what happens. 0, 1, 4, 9, something like that. Okay. And then remember how y is equal to 2x squared? Y equals 2x squared. So I'm still playing off the same equation. I'm still going to graph y equals 2x squared, exactly like I did before, but just on a set of manipulated axes. Okay? So that'd be 0, 2, 8, 18. I mean, it's the same values as I got before, right? No different. Okay, so I wonder what this is going to look like graphically. Okay. Now, my x, well, the horizontal axis is actually not an x-axis. It's an x squared axis. So try this. 0, 3, 6, 9, maybe something like that. Well, I really care about the points 1, 4, and 9, right? 0, 1, 4, 9. Okay, like that. 2, 5, okay. And then y, I better scale the same as I did before, 5, 10, 15, 20. Okay. Okay. I plot these points down on this manipulated axis. So you've got the point 0, 0, that's where it was before. Got 1, 2, it's right about there. Got the point 4, 8, which is right about there. I got the point 9, 18, which is right about there-ish, like that. And oh, look at this. All these points line up on a straight line. Okay? So this parabola has effectively now been linearized. Okay? And that's how you can confirm that it is, in fact, the original shape was, in fact, a parabola, because by specifically squaring the x-axis instead of cubing it or putting it to the fourth power or something like that, which would indicate maybe a different kind of curve. Okay? You guys get that? Right, check out? Okay. It's one of those things you have to think about a bit, digest, sleep on it, go back, look at your notes. Okay? But we're about to apply this to your guys' lab. Okay, get ready to do that? Okay? Okay, yeah. Flip this page here. Okay, so we'll back to your guys' lab page. Okay. All right. Right, we did math first time, got that relationship. We did this the first time, got a bunch of points that looked like they were straight lines, and we started thinking about it, think it's probably part of a curve that looks like this. Okay, now we're about to do the big one, and this is the most important one. So it says distance versus time squared. So I'm going to put distance in centimeters on the vertical axis, just like before. Okay. But on the horizontal axis, now this is the one that's going to be weird. It's not going to be time. It's going to be time squared. Okay. And in this class, we also care about units. Right? Remember, it's not just the numbers. There's always units attached to these numbers. What do you think the unit is for time squared? Second squared. Yeah, 6 squared seconds. which is a really abstract idea. So what does AD mean physically, right? But watch what it'll do to the graph, right? But to do that, I need to flip back over to the Excel page. Right? You guys ready to get this? Right, so you can start to scale this, start at 0, 0. You're about to scale that based on what you see on the Excel page. When we go back to present, screen to share, right? Now the computer flip over. Right, so this is where we left off. This was the last one, right? So look to the next one, to the how x versus t squared. Right, so I pre-programmed Excel to automatically create this graph for us. That's what it looks like. Hey, look at that. And if I right click on one of these, go to add trend line, look at that. It's a straight line that does in fact go right through the origin. Right, which makes sense because you started the car at time 0, location 0. In fact, I'll even display equation on chart because we're going to have to interpret this equation. Okay. So scale the velocities, just like that. Put those points about where they go, and then the line does fit. Just throw down your ruler, go zip, your line does fit. Which is the best way to do it, right? Are you guys going to connect those points dot to dot, like dot, dot, dot? No. You're looking for an overall trend line, right? Why is that? If you connect it dot to dot, you'd be saying, I know very precisely, specifically that there can be some like weird changes depending on what. No, that's not what it's saying. The reason those dots don't exactly line up on the line is because there's a little bit of measuring error, right? Exactly where do I start off the stopwatch, right? It's like that. Which is expected, but that is a really good line right there. That is a really good fit. Okay, good. Okay. While you guys are finished copying that down, tell you guys a little bit about the philosophy behind this too. So one of the powers of science is that it has predictive power, right? If you go back like 1,000 years ago and say, what's going to happen in the future? I don't know, let's talk to the crazy old person over there with like a magic ball or something. But then science comes along and you realize, hey, you can actually create a model of the universe, which is what you guys did with that lab yesterday, right? And you can make certain measurements and maybe you could put together physical equations so that the next class comes in and they start rolling their cars down the incline since it's the same angle and all that. Right? You can say, if you tell me how many seconds this car has been rolling for, I can tell you exactly how far it's rolled. I can predict. I have predictive power. And that's the predictive power of science and physics. Okay? In this case, so many seconds roll by, square the number of seconds, multiply by the slope. You can say, boom, I know that many centimeters it would have rolled. Okay? Or vice versa, you know how far it rolls, you can say, I can tell you what the time is on your stopwatch. Okay? So how are we going to interpret this? Well, see how this line goes basically through the origin just graphically? Okay? Let's look at this equation and see how that lines up. Is this in the form y equals mx plus b? It sure is, except x in this case represents the square of time, y is how far. You guys get that, right? That intercept there, is that basically 0? That negative 0.5, is that basically 0? Yeah. What are the units on this anyway? What if it wasn't 0? It's negative 0.5 what? Centimeters. Yes, centimeters. Okay. Same story for the last one. Remember, it has to jump like 100 centimeters. Okay. Okay, but that's basically 0 for all intents and purposes. It's so close. It's just a matter of like where exactly. Whoever was signing this only missed the stopwatch by 1/2 of a centimeter. That's crazy accurate, isn't it? So really good job on that stopwatch. Okay? But how about that 27 number, the 27.5? Are there units attached to that number? And what are the units? Rise over run, right? You guys know that's the slope. Like the slope is rise over run. What's the rise of this graph? What units? Centimeters. And what's the run? Second squared, right? So you think that this number 27.5 is actually 27.5 centimeters per second squared, right? Right? Okay. Everybody copy that graph down? You guys finished? Ready to move on? Okay. Let me flip back over to my screen. Please stop sharing the screen for the representing. Okay. Okay. So, now I'm skipping some steps myself here, but just to cut to the critical part, you guys have basically a straight line relationship. You guys have, of course, all your points and all your numbers, right? And we're getting, this has a slope of 27.5 centimeters per second squared. That's the slope of that line, right? Okay, so that number of units, okay? Which is gonna bring us in for the win here. Guess this very last question says, write an equation relating distance, mass, and time for the given ramp angle, right? what was your guys' ramp angle? Yeah, so some of you guys got 4, some of you guys got 5. So you put either 4 or 5 degrees here. Either one, okay? Uh, so that's basically x, right? Like x equals. Okay. How would you guys finish off this equation? How is mass included? Doesn't matter. Has nothing to do with motion parts. So I'm not even going to include mass. Okay. How about time? You guys think it's 27.5 centimeters per second squared? Have to put the units because physics, science class. Okay. Multiplied by what? Is it t? It's what? T squared. T squared, right? Right? So, for example, next class comes in and they're looking on the stopwatch and they say, that car was rolling for 1.4 seconds. Can you predict exactly how far that car rolled? You plug in 1.4 seconds, square that. That's 1.4 seconds squared. Multiply by 27.5 centimeters per second squared. Hey, did the second squared cancel out? And it leaves you with centimeters. And you can report exactly how many centimeters that car rolled. Get it?
Are there any equations that mass actually does matter for in this class? Because the spinny thing doesn't matter for the mass, and this now doesn't matter for the mass, and the speed of falling doesn't matter for the mass.
Yeah. Okay, so yeah, good question. It looks like I guess I gave you some examples by now that math tends to cancel out quite a bit in this class, doesn't it? Right? Yeah. So it will matter for some equations as we get going on in this class, but that is a really common thing for math to cancel out. So that's a really good observation. Yeah. All right. Is everybody good with all this? Okay, got a conclusion, which is that equation right there, which answers the original question. So we're all good on that. Okay. Now you guys also have that lab write-up on the back. You guys know this lab write-up? Okay. Now, remind you guys why I'm giving you guys this, what all this is about. We'll probably do this about every lab. Okay. So there's these 5 parts: right? The question, measuring tools, data gathering procedure, analysis, conclusion. Okay. I put this together based on reading so many experimental design FRQs from AP. There's just like certain things they're looking for, right? Now, when you guys get the exam in May, you're gonna have. Let me tell you guys how the exam structured. There's 2 halves. There's a multiple choice half, which looks a lot like your guys' progress checks, and there's an FRQ half, right? So each is half. Right? The FRQs, there are 5 questions, 5 FRQs. Right? One of those FRQs will be an experimental design question. They're going to say, like, figure out, I don't know, how long does it take a car to roll down a ramp? And you're going to have to design an experiment. You might get that question, and you just do exactly what's on your paper right now, right? And there's always a thought process that AP has, and it's pretty much this right here. It's just like these points. Right? There's also a rubric that they grade on. So we're going to practice that right now. We're going to pretend this is an AP exam. You did all blah, blah, blah. Okay. You guys see a color pencil on your desk? It's probably either green or red or something close to one of those colors. Okay. Pick that up. You're going to have to grade yourself. So I put together what I thought was probably pretty close to what AP would come up with. Go ahead and grade yourself. Now, this is going to be out of 12. Same thing on AP exam in May. This is going to be one of the 12-point FRQs, which is one of the bigger value FRQs. The other ones are 7. So this one's going to be 12. Right. Score yourselves by the end. Do it completely honestly. So if you get 2 out of 12, write 2 out of 12. If you get 10 out of 12, write 10. If you get 7, write 7 out of 12. However you do on this, it's fine. It's not going to affect your class grade. But I do want you guys to be thinking actively about this. You'll get better at this as the year goes on, right? Right? So it's like a total swing and miss, and you have no idea how to put this together, then, well, you will by the end of today. Right, so remember there were 2 different labs going on. So I'll do side by side to start with, okay, then I'll go through these one by one. Okay. You guys can't really read that. I'm just going to focus on one of them. Okay. So one of you guys had the question, what's the relationship between mass and time for a car rolling down the incline? Controlling for distance and angle and everything else, okay? Half of you guys had this. If you didn't have that, then you had the question, what's the relationship between distance and time, controlling for mass and angle, okay? Okay, so let's do one at a time. Start with the first one. Okay, so mass versus time. And remember, you guys found that there's no relationship. Okay, so measuring tools, this is something AP cares about. Do you know what measuring tools are involved? 1 point for each one of these. If you mentioned a scale or a triple balance beam to measure the mass of parts, give yourself a point. If you mention meter stick, give yourself a point. If you mentioned a stopwatch or timer, give yourself a point. If you mention a protractor to determine that angle, give yourself a point. Or, tell you what, there's actually an alternate to this. Could you guys can you guys think of a way to solve for that angle of incline? This right here, without a protractor. You can figure it out. How can you do that? Inverse tangent. Yeah, Mauricio, you guys hear Mauricio? He's saying, hey, if you measure, well, I don't know, this height and maybe this leg of this triangle, this looks like a right triangle, take an inverse tangent of this over this, or an inverse sine of this over this. Either way, right? So if you said that instead of the protractor, then I'll count that as a point instead. Okay. Data gathering procedure. Now this section is all about taking these measuring instruments and measuring specific variables and just explaining what they are. Okay? So one point, well, actually, never mind. Start from the beginning here. Set up an incline at a shallow angle above the horizontal for a toward car to roll down. Now, these points always add up to 12, so I try to do something like that. Sometimes that's worth a point. So I didn't do it on this one, but sometimes they say if you do a brief description of the setup, yeah, Ed?
Will we need to put this down in our lab notebook that you said we might need?
Yeah, so here's the deal with lab notebook. If you want to keep everything in the lab notebook and just turn the whole notebook, and I can check it off and get it back to you, that's okay. What's probably easier is if you just do like your single sheets of paper, turn that in, give it back to you, and you can compile the notebook yourself.
I just care about this specific lab. I wasn't really here for most of it.
Oh, yeah, I know we got a lot of quarantining situation going on too, so students miss stuff. So, yeah, if you,
Is it worth saving that? I'll have it like that.
do you have a write-up going?
Do I have a write-up going?
How much do you have?
I mean, I got the graphs down yesterday.
Okay.
I didn't do it in the back.
Okay, just follow along here, just write these down like as notes, just so you have a model for the future. Yeah.
Okay.
Yeah, okay. I think it'll work out pretty good. Tell you guys what, for labs, what I usually do, because labs usually require a lot of teamwork and a lot of equipment that have to get out and time and whatnot. So, and I know a lot of you guys are going to end up getting quarantined at some point in the year. So, what I usually do for labs is if you totally miss it and you just weren't here for it, I'll just give you an exempt. And if that happens for like, one or two labs, it'll be okay. It's probably not going to affect your grades that much anyway. I usually tend to grade labs pretty light, so as long as you have everything there, you have the graphs, you have the write-up, you do what I say, then you just get credit. It's usually pretty easy anyway. So it works either way. So if you're here, you show up, you do it, helps your grade. If you miss it, totally weren't here, then I can exempt one or two, and that's okay. Yeah. All right. So back to this. Now using these measuring tools. So using a protractor to measure the angle. If you mentioned application of the protractor, give yourself a point. Right? Or if you did that inverse tan or inverse sine method. That counts too, alternatively. If you mention the triple beam balance, measure the car, and you say that, I'm going to measure the mass of the car, give yourself a point. Okay. If you mentioned fixing some specific distance, I've got 200 centimeters here, but it could have been whatever you made. Okay. Said how you use the meter stick, that's worth a point. If you mentioned timing the car with a stopwatch, so that process of timing with a stopwatch, give yourself a point. Okay. Ooh, here's one that AP likes a lot. You guys remember how I had you guys do 3 of the exact same scenario and then take an average? That's almost always one of your points for the AP exam. By the way, between your multiple choice and the FRQs, as you're tallying up points like this, if you get about 30 points, that puts you right on the edge of passing, about 30 points. And this is almost always one of the points right here. Right? So just mentioning multiple trials to reduce random error. Right? Multiple trials, that's the point. Then I've got here, attach a small lab weight to the car, repeat step 336, do this for 5 different car masses, that's showing that mass is an independent variable. Depending on how they score this, that could be a point. I didn't do it on this one, but that could be. Okay. Good score. All right, then data analysis. You would have plotted distance versus, that's not the right one. Here it is, this one, right. Plot mass versus time to roll down the incline. So a point for that if you said graph mass versus time. And then if you determine that the fact that it was a vertical line indicates that there's no relationship, give yourself a point, which also was the conclusion. Conclusion is there's no relationship between mass and time to roll down. Okay? Mass has nothing to do with the motion of the car. Okay? All right, so that's 12. Tell yourself out of that. In the meantime, let me show you guys if you have the other version of lab. So just very similar. So now the question is, what's the relationship between distance and time? But it's the same measuring equipment. So scalar, triple beam balance, meter stick, stopwatch, protractor. Give yourself a point for each of those. Right? Then data gathering procedure. So how to use these things. So basic lab setup, set up a shallow incline, let the torque bar roll down. Brief description. Use the protractor to measure the angle, record in degrees, 1 point for each protractor. Right. Use the triple beam balance to record the mass of the car. That's a point. With the meter stick, measure some distance, give yourself a point. Right. Now, I was copying and pasting here, so I put fixed, but it actually should not be fixed for this version of the lab, so oops, cross that out. Okay. Release the car from rest, the top of the incline, use the stopwatch to measure how much time it took. So 1 point, mention application of stopwatch. Repeat this 2 more times to take an average. So if, by mentioning multiple trials and taking an average, that's worth a point. Right. Then this last point I got here is not an AP point, but just a lab step. Change the rolling distance to some new distance. Repeat steps 5 and 6. Do this for 5 different rolling distances. Okay. Okay. So your procedure should look something like that. Okay. You guys good so far? Okay. Then finish this off. All right. Now you want to. Right, now this page comes in. Okay. Plot distance versus time. Okay. Now that's the one that came out to like a parabola shape, right? So here's the next line. Because the shape appears parabolic, linearize the graph by graphing distance versus time squared. Okay. Now, of course, by May, you'll know these equations back and forth, so you would know for sure that's a parabola. So you could say pretty definitively to do that. Okay. And then AP might assign points something like this. By mentioning linearizing this graph, distance versus time squared, that could be a point. Or if you said there's a actually, here's the second point. If you mention a parabolic relationship between just distance and time, okay? So there's 2 points. Okay? And I do have one more thing in brackets here, which we haven't talked about yet, but this makes sense in a few weeks and in the future. And AP can totally ask this question by the time you already take the actual AP exam. It turns out that the slope of that graph, remember how the slope of the graph came out to be like centimeters per second squared, right? Which is like something to do with a rate change in motion, right? That's the same unit as acceleration. It turns out, though, that that value only represents half of the acceleration of the toy car. Think about that. So this one half acceleration. Yeah. Right. Why is it off by like a factor of a half? We'll talk about that in the future, but same idea. Right. Conclusion: there's a parabolic relationship between the distance the car travels and how much time it takes to roll down. Okay, something like that. Yeah, Eddie?
In the future, will we be asked to create 2 graphs, or will we linearize our data by a default?
So actually, what they tend to do is so for labs, sometimes I'll leave it a little bit more open-ended and have you guys figure out exactly how to do it yourselves. On the AP exam, they tend to direct you towards doing something like that. Like how they actually tend to ask this question is, how can you linearize the graph? And you say, oh, well, I'll do distance versus time squared. Right? Or if you think really close, if you actually do the square root of distance versus time, that would also linearize the graph, and they would also accept that. There's usually more than one way to linearize it.
They'll tell you to linearize it if you have to linearize.
Yeah, that's usually how they prompt you to do that. Okay, okay, so you guys get that? Okay, so score yourself out of 12. So hang on to that for about 10 minutes. I'll have you guys turn that to the grade tray as you leave for lunch. Okay? So have that on your desk. Okay. You guys good? Good question? All right. You guys ready for some notes? Some linear motion notes? All right, I'm going to get as far as I can today, but I have to finish these tomorrow, but as much as we can, like 10 minutes. Okay, so if you're thinking about how many variables we're juggling here, I got X, I'm not going to talk about mass for a while. Kinematic motion, I really care about, well, let's say we're not going to be really talking about mass yet, but distance, time, maybe we got speeds going on, maybe this car is speeding up and I care something about that. Turns out there's 5 variables that we're going to end up juggling around. And as a mnemonic device, I like to say tax VV. I'm going to leave some space so I can define some of these things, especially the A. Leave some space after that. Tax VV. I see tax VV. Okay. Okay. So T, these all refer to variables. T refers to time. That's going to be measured in seconds. Well, you guys know what time is, tick, tick. Okay, so moving on. Okay. Well, almost. There's one thing I want to say about time. It's a scalar value, which means that it doesn't have any three-dimensional motion. Like, you can't say, like, that time was moving at 45 degrees. No, it's just time. It has a magnitude, but no like direction, things like that. Okay. These other four variables are all going to be vector values. These are all vectors. Okay? Which means that not only do they have magnitude, but also a direction that is important. Sometimes the direction is implied, like if you're moving in the forward direction, sometimes they don't explicitly type that out, but you can imagine in your head. Okay. Now I'm going to skip this A because that's the most involved one. I'm going to come back to that. X usually represents displacement. Sometimes I say distance, which is technically the scalar value. It's going to be meters. Okay. Lots of other characters used for displacement. Sometimes you'll see Y or H or R or S sometimes. That's just tricky because it looks like 5, but V, what do you guys think V stands for? Velocity. Now that's like speed, like how fast, but also with the direction. That's important. Now, dropping that car down that incline yesterday, was the car speeding up, going faster, faster, faster? Right, and usually how the problems are presented to you is that usually there's some time interval that is taken along, and there's maybe a starting velocity and an ending velocity. Like yesterday, your guys' starting velocity was what if you release the car from rest? 0, right? And then maybe it was crossing the finish line with something else. And these two V's refer to those, just the starting and the ending. I don't really care about anything in the middle. So I'm going to do a subscript not on that one and a subscript F on this one. All right. Let me give you guys an alternate for the V naught. I'm going to say or V sub I. Sometimes you see that. AP a lot of times like to switch out and do sub I. It means initial velocity. Initial velocity. That's going to be measured in meters per second. V sub A stands for final velocity. And that'll be in also meters per second. Right? Again, this is for some particular time interval, like the car rolling down the incline. This could be at the top of the incline. This could be as it's crossing the finish line. Right? Now, of course, it had a million different velocities from start to finish. I don't care about those. I just care about the starting and ending. Okay? Right. Which brings me to acceleration. Is that? Fill up some space there. So acceleration. Right. Now this has a unit of meters per second squared, which might look remind you of a lot of that graph, that last graph you guys made. Remember, it was like centimeters per second squared. And say, that looks a lot like that, doesn't it? Right. This is the rate change of velocity. Right. And here's a formula for it. Acceleration is equal to final velocity minus initial velocity divided by time interval. That would be rate change of velocity, wouldn't it? You guys see that? All right. Which also makes sense for the units. If you're wondering meters per second squared, maybe that doesn't 100% sit well with you. Right, well, maybe here's a little bit better. If I had some number of meters per second that it changed, went from say rest to some number of meters per second, and I say it took so much time for that to happen, right, like rise over run on that graph, right? Meters per second per passing second. Maybe it's picking up, maybe it's speeding up. Hey, meters per second per passing second. Can I combine the second units, make like meters per second squared? Okay. Guess why that checks out with that unit, right? Guess that? Okay. I threw a question to you guys first week of school. It said if you're sitting in the passenger seat of a car and you're blindfolded, can you feel if the car is going 50 or 60 or 70 miles per hour with cruise control? No, you can't tell. Can you guys feel the earth spinning right now, 1,000 miles an hour? No. Do you feel velocities? No. Velocities are always relative to something. You can only move so fast relative to something else. But you can feel a car moving around. Feel something about a car. Feel this going on. Right? So, what can you do in a car that you can feel some kind of change going on? Gas pedal, or the brake, or the steering wheel. Okay. Now, next few weeks, we're just going to focus on the gas pedal and the brake because just linear motion, forward, backward sort of thing. Maybe we'll go to reverse sometimes. Okay. We'll bring in the steering wheel a few weeks from now. Okay, so we're not ready for that yet, but we're going to work up to that point. Okay. Now, it turns out, give you guys a little trick here, okay, that if you have any three of the above variables, you can solve for the other two. What do you mean by that? Give you guys an example. Yesterday, when the cars down the incline, you guys did already tell me that the initial speed of the car was 0. Right? Sometimes I'll say speed for velocity, but you guys know what I mean, right? Velocity just has a direction, but whatever. Right? Car started at rest. Got this number. Check, 0. Right? You guys had some meter sticks, so you knew how far the car rolled, and you measured with the stopwatch the corresponding time. Hey, is that 3 things? Initial velocity, distance, time. That's three values, isn't it? Right? So, do you think that from your lab data, in principle, there's enough information lying around that you could figure out the rate that the car was speeding up for all that to happen? Yeah, right. That's not exactly the slope of distance versus time squared, but it is related to that. It's off by a factor of like 2. So I guess about that. And do you think there's, in principle, enough information lying around that you could solve for how fast the car was crossing the finish line? I bet there is. Right? I bet we need some equations to tie these 5 variables together. Right, you guys ready for some equations? Right. Let me start with one because I sort of have one started right here. You guys see this one? Let me start with this one. Right. So you guys know that acceleration is a rate change of velocity. Remember, this is the one that you feel. Actually, you feel forces. Forces cause things to accelerate, but we'll start from that point. Right. I'm going to rearrange this into a form that I usually write this equation, which is in terms of final velocity. Just have it over the years. Right. So, can you guys do algebra? Can you guys solve for VF? Cross multiply of the t, acceleration times time is the difference in velocities, start to finish. Right? And then final velocity, therefore, is v naught plus at. Okay? That's one of your equations. There. Okay. All right. Tell you what. I will give you guys notes tomorrow, but I'm just going to flash these up here from last class because otherwise we're running out of time. Okay. So, can you guys say distance equals speed times time if you're at cruise control, just not speeding up? Okay. So, cruise control, distance equals speed times time. Okay. And if you are, let's say you drop something from rest, edge of a cliff. It's going to do this x equals 1/2 at squared. I'll talk about this more tomorrow. What if you combine these two? Because what if you don't start from rest, and what if you are accelerating? Right? So you go to the edge of the cliff and you throw a ball down, or you guys give your car from yesterday a push, and then it rolls down after you give the push. Right? You can combine it all together, and it's going to make the second equation. Right? So got this one, talk about more tomorrow. Right? And then there's a third equation that's actually incredibly useful. You can get from a system of equations in the first two, is that with those 3 boxed equations, I mean, the dashed ones are simplified scenarios, but with these 3 boxed equations, you could solve every single one of these box paper questions. Okay? Right. Probably do that. Pick up tomorrow, and I'll give you guys those notes, and we'll go on from there. All right? You guys good so far? Right. We got about 20 seconds. So before you walk out the door today, you guys see this break tray here? See the break tray? You guys got to turn in your lock to the break tray, right? Lock to the break tray.
You think you could